Okay. So now we'll be moving towards your double line to ground fault, and this corresponds to the fault between two lines and then your ground. Okay, so your two lines are also involved with respect to your ground. So here you can see, first you have to draw this diagram. First you have to draw this diagram. Okay, three lines, and over here your fault impedance is ZF, and as the title suggests, the fault occurs between two lines B and C, and it will be connected towards your ground. Whereas in the previous case, in case of a line-to-line fault, it was between only your two lines. Now you have to consider your ground also. Okay, yet there lies your IA to be 0. As such, what happened in your line-to-line fault? So there also your IA was 0. I told the reason behind that, since your current will be always finding the least resistance path, most of the current will be flowing through your B and C. Okay, so this is where the fault occurs. Basically, can take considered to be a short circuit fault, and across this, the resistance will be very limited, and the current will be shooting up very high. Okay, and as I said, first you have to write down the characteristic equation. As per that, the characteristic equation is IA equal to 0. So it is first characteristic equation for this particular fault condition. And after that, over here, the voltage potential drop will be VB will be same as that of your VC. Since you have to consider this with respect to the current and not with respect to your two lines. Okay, you can see the potential drop. The potential drop we have to, if you're taking this with B and then your ground, means it is one thing. And the another one, if you have to consider with respect to a C and the ground, it is another one thing. But what happens is that the potential drop will be the same for these two faults that between the lines. Okay, that's what will be getting VB equal to VC. Okay, and yet what happens is that the current flow will be an additive of this both the things. So here you can see, if you're applying the KCL at this particular node, it will be the summation of your IC and then IP. So that's what over here. Okay, and this will be particularly equal to 3 ZF into IA naught. That is your zero sequence component. So here, what I will be saying is that there lies your zero sequence component, but your current flowing in the particular A phase will be 0. Okay, but this zero sequence component lies. Why in the sense means your ground comes into effect. Whenever your ground is coming into effect, you have to consider your zero sequence component. Okay, so that's what here. So this is what zero sequence component. So 3 ZF into IA naught. Okay, so this is one of the characteristic equation. And as I said, after writing a characteristic equation, you have to move towards your symmetrical component matrix. So first you'll be writing with respect to your voltage. So this is a basic symmetrical component matrix thing, and after that you have to determine the voltage based upon this characteristic equation. So as per the characteristic equation, if VB is same as that of VC, that you can just replace it. So after that, you have to get the value of your VA0, VA1, and then VA2. So from the characteristic equation itself, you have determined that VB equal to VC. So what happens is that your VA1 will be same as that of your VA2. That is, the potential drop is the same. So from this also you can say that both your positive sequence component and your negative sequence component, VA1 and VA2 are parallel to each other. Okay, that is, whenever they are parallel to each other, the potential drop will be the same. Okay, basic law. So from this you are determining your VA0. Okay, VA0 you have to determine. So VA0 is the summation of these 1/3 into VA plus VAB plus VB. So that lies 2 times of VB, and after that VA1 is same as that of a VA2. So over here, another thing what you have to see is there comes another one, A operator term, A plus A square. So A plus A square corresponds to your J root 3. Okay. and this we can consider to be the fifth equation. So from your fifth and fourth equation, what you can have is that so here VA naught minus VA1 they are doing, that is they are subtracting your VA naught with respect to your VA1, subtracting your VA naught and then VA1. So VA naught minus VA1 if you're subtracting means you'll be getting an equation like this. And over here again you can take this minus out and you can take a plus a square and you can apply the value. So you'll be getting around 1 by 3 into VB. So this 3 and then 3 will be getting cancelled out. Okay, so if these two gets cancelled out means finally you'll be getting the symmetrical component as VA0 minus VA1 equal to only VB. So also you can notice that this equation will not having entire symmetrical components. So there lies this VB. So you have to change this VB. Already we have know the value of this VB from this characteristic equation from here. So this you have to substitute over here. So it is 3ZF into IA0. So here comes your zero sequence component. And from this zero sequence component, VA0 can define as VA1 plus this value. So that is you are bringing from your left hand side towards your right hand side and keeping your VA0 at your left hand side. So after this, you can draw the sequence diagram. As I said, it is very obvious that both your positive and negative sequence components will be in parallel to each other. So it is shown in the sequence diagram itself. So after that, you have to connect this ZF in series. So this will be in series, and you have to draw your zero sequence component. So this corresponds to a zero sequence component. And from this, you have to determine your positive sequence component in order to find your IB or the fault current. Okay. So here, in order to find that, what you can see is that so here you can see the EA. So this is your voltage drop, and the voltage. So this is your voltage rise. This EA is the voltage rise, and the voltage drop. How you can consider is that you can consider it by this Z1 plus Z2. Okay, which is this Z2, which is in parallel with your Z0 and then this 3ZF. Okay, so these two are in series. Okay, I hope you are able to understand. These two are in series, and this is in parallel. Okay, and this particularly forms out to a particular impedance, and that is what this particular impedance. That is, this Z2 is in parallel to these two impedances, not to only to this Z0, and this you can consider to be in series. Okay, so that was this IA1 equation. So we'll be if you are finding the effective impedance, you'll be arriving at this particular equation, seventh equation. So now we have got your positive sequence, and to get into a particular relation, what happens is that this IA1 is there, right? This is particularly converted into a matrix form. This is converted into a matrix form, and this is eighth equation represents the matrix format or the analytical form of the previous above seventh equation. Okay, you might be somewhat confused, but what happens is that if you are multiplying and arriving at a particular equation means you'll be getting this same seventh equation. Okay, so there won't be ZF, but there is VA1. Okay, so this VA1 value you can substitute from a VB, and finally you'll be getting ZF. Okay, so this seventh equation is what written the form of eighth equation. It is for simplicity purpose. You can just simplify and see. Most of the terms will become zero. And there lies your IA1, and then your Z1, Z2 will be there, and your ZF will also be there. So after that, for simplifying purpose, you will be writing your VA naught, VA1, VA2 in terms of your EA. That is your voltage rise. So in order to write your VA naught in terms of your voltage rise, uh, so this is one will be can get this from your characteristic equation. So this is nothing but this particular term corresponds to your VB. So this is your that is nothing but VA1, VA2. So this will be your VA1 plus 3 times of ZF into IA naught. Okay. So this is the equation will be coming out if you are representing your VA naught, VA1 in terms of your EA. Since here is EA, you have to convert everything in terms of your EA. That is the voltage rise. So after that, you will be multiplying on both sides with your Z minus matrix. It is a matrix. So it consists of zero sequence, positive sequence, and then your negative sequence. So you'll be multiplying with this on both sides. And finally, you'll be getting, after the multiplying this on both sides, and then you have to pre-multiply with the matrix of 1, 1, 1. So it is a row matrix. So why you are multiplying with a row matrix means in order to get a single element, single row element. Okay, so between these two steps, there lies nearly 2 to 3 steps in between. So what happens is that you can just solve it by yourself and see. So from this, it is very easy to have this equation, and after this equation, you can just multiply with the 1, 1, 1 on both sides, and you will be arriving at this particular equation. Okay. So if you want to get a clear idea about the in between steps, you can just refer the book what it is in the Google Classroom. Okay, there they might have given clearly. Okay, and after this, this is the ninth equation, and from this, you just have this ninth equation as such, and then you already know that both your VB is same as that your VC, and through that you can take your positive sequence is same as that of your negative sequence, and from here you have to substitute the value of your positive sequence, and then the negative sequence also you have to substitute it, and you will be getting the value of you also know that IA1 plus IA2 IA naught plus IA2 plus IA1 will be equal to 0. From that, you have to determine your IA2. And now you have to substitute this IA2 value over here. So if you're substituting means, you'll be getting EA minus Z1 IA1, which is equal to Z2 into IA naught plus IA1. Okay. And from here, you have to bring this EA to this side. Okay. You have to bring this EA to this side. So this Z2 and IA naught will be at this side, whereas all the other terms will be coming over here. Okay, from this you will be defining your IA naught. So IA naught will be defined. So Z2 will be coming over here. So IA1 is common in these two parameters, so you'll be taking common out. Okay. And after this, you have to substitute to this IA naught value over here. We are completely making this ninth equation in terms of your IA1. You have to find your IA1. Okay. So for that, we will be completely changing this ninth equation in terms of IA1. So you have to find IA naught first. So that's what we have found out, and we are substituting in your ninth equation. Okay, and from this, you can easily define your IA1. So IA1 finally will be getting as EA by Z1 plus Z2, Z0 plus 3 ZF. So from this, what you can arrive at fault current IFS. So IFS is nothing but here it will be additive of it. So this we have already seen. So it will be additive of your IB plus IC. So which is equal to 3 times of your IA naught. Okay. So this is what with respect to your double line to fault. Okay, you don't get confused. You just move through a step-by-step procedure, and mostly in this you can expect problems. Mostly can expect problems for your university exam. Okay, I'm telling with respect to university exam. With respect to university exams, you can also expect கூப்பிடுறேன் சார். சரி சார். ஸோ